So breadth-first search, the priority is take off from the fringe, the queue, the thing that has the shallowest, shortest plan so far in terms of number of steps. Okay, let's have a look how breadth-first search is updating queue, visited, open list, and expanded list, closed list during the process. If you remember, breadth-first search is using queue data structure, first in, first out. So we are going to start with S. Our goal is to reach the G and return us the shortest path, shallowest path. Whenever we put S in our queue, it is going to be directly in our visited list, but not yet expanded, because we haven't expanded S yet. We don't know the children yet. Whenever we expand them, they are going to be expanded. After S, there are two options, A and B. They are the shallowest one. We start with A if we are breaking the ties alphabetically. SA and BS. Now it is time to put S in expanded, A and B in our visited. Now the question, is A our goal? No. Does it have any children? Yes, it has two children, C and D. Are they in the visited list or expanded? No. So we can expand them and put at the end of the queue. So BS will be the first, CAS, DAS. Now it is time to open B. That is the shallowest one. CD are in our queue, waiting for their time to be explored. After B, there are two options, D and G. First we ask, is B our goal? No. Does it have children? Yes, D and G. Are they on the visited? D, yes. So we are not going to expand this one. You see how visited are saving us to expand too many nodes. Even for such a small world, small tiny graph world, it is saving us time and space. When things come uglier, when we have a huge world, it is gonna save a lot of time and space for us. This visited list is very strict. It doesn't accept any alternative paths. It is just cropping it. Sometimes it is not good. Expanded list, it is leaving the paths to open. So it is not as strict as visited. Now it is B's turn. After we D and G, we are just gonna open G here. GBS at the end of the queue. Now it is turn C. C is goal? No. Does it have any children after C? No. So we are just going to we are here. We are just going to remove this path at all and put C in our expanded list. So we are not going to come back and visit that one again. We don't need to lose time. DAS and GBS just remaining one. After D, is there anywhere to go? Yes, we have C and G, but both of them already in our visited list. So we can put D in our expanded list, not to repeat it again, and GBS will be the last remaining path. We ask the question again, is G our goal? Yes. Now we can return GBS as a solution. As you see, there are three solutions here, SADG, SBDG, and SBG. As we expected, breadth-first search returned us the shallowest solution. Now breadth-first search, is it complete? Yes, if solution exists. Is it optimal? Yes, the first one found must have shortest path. The time is exponential. This is branch factor, and this is the depth, big O, B power D. You have to, in the worst case, you have to explore all the nodes. Space is same again. You have to explore all the nodes and put them all in the queue. The shallows will be in the queue. Implementation, it's going to be first in, first out queue. So that is breadth-first search. Before starting our today's lesson, I want to show you some search algorithms and how they are looking for their goal in a maze. This is our first sample. We are green one, it is looking for the red square here. Let's look. It is going slowly. It looks like it doesn't know where is the goal and searching this maze layer by layer. As you see, it goes layer by layer. It is almost there. I guess it will find it. Now it found it, but it didn't stop. It is going for the second turn and it stopped. Yeah, this is in fact the shortest path from this point, and it found it. But it searched many places to find this one. Definitely it doesn't know where is the goal.